A lightning rod or lightning conductor is a metal rod or metallic object mounted on top of an elevated structure, such as a building, a ship, or even a tree, electrically bonded using a wire or electrical conductor to interface with ground or earth through an electrode, engineered to protect the structure in the event of lightning strike. If lightning hits the structure, it will preferentially strike the rod and be conducted to ground through the wire, instead of passing through the structure, where it could start a fire or cause electrocution. A lightning rod is a single component in a lightning protection system. Lightning rods are also called finials, air terminals or strike termination devices. The lightning rod requires a connection to earth to perform its protective function. Lightning rods come in many different forms, including hollow, solid, pointed, rounded, flat strips or even bristle brush-like. The main attribute common to all lightning rods is that they are conductive. Copper and its alloys are the most common materials used in lightning protection. History: the lightning rod was invented by Benjamin Franklin in North America in 1749, and in Europe, probably independently and as the first grounded lightning rod ever, by the Czech priest Procoptive in Bohemia, in 1754. As buildings become taller, lightning becomes more of a threat. Lightning can damage structures made of most materials as the huge currents involved can heat materials to high temperature, causing a potential for fire. Sri Lanka: some of the most ancient lightning conductors can be found in Sri Lanka in places like the Anuradhapura kingdom that dates back thousands of years. The Sinhalese kings, who mastered construction of stupas and advanced building structures, installed a metal tip made of silver or copper on the highest point of every building to conduct any lightning charge. In many parts of the world, ancient Buddhist monuments have been destroyed by lightning strikes, but not in Sri Lanka. Russia: a lightning conductor may have been intentionally used in the Leaning Tower of Noviansk. The spire of the tower is crowned with a metallic rod in the shape of a gilded sphere with spikes. This lightning rod is grounded through the rebar carcass, which pierces the entire building. The Noviansk Tower was built between 1721 and 1745, on the orders of industrialist Akin Demidov. The Noviansk Tower was built 28 years before Benjamin Franklin's experiment and scientific explanation. However, the true intent behind the metal rooftop and rebars remains unknown. Europe: the church tower of many European cities, which was usually the highest structure in the city, was likely to be hit by lightning. Early on, Christian churches tried to prevent the occurrence of the damaging effects of lightning by prayers. Peter Alwarts advised individuals seeking cover from lightning to go anywhere except in or around a church. In Europe, the lightning rod may have been independently invented by Czech Premonstratensian priest Procoptive between 1750 to 1754. Divya then placed the first grounded lightning rod ever in his garden in Parham registered trademark Amatus near Znojmo in 1754. United States: in what later became the United States, the pointed lightning rod conductor, also called a lightning attractor, or Franklin rod, was invented by Benjamin Franklin in 1749 as part of his groundbreaking exploration of electricity. Although not the first to suggest a correlation between electricity and lightning, Franklin was the first to propose a workable system for testing his hypothesis. Franklin speculated that, with an iron rod sharpened to a point, the electrical fire would, I think, be drawn out of a cloud silently, before it could come near enough to strike. Franklin speculated about lightning rods for several years before his reported kite experiment. This experiment, it is said, took place because he was tired of waiting for Christ Church in Philadelphia to be completed so he could place a lightning rod on top of it. In the 19th century, the lightning rod became a decorative motif. Lightning rods were embellished with ornamental glass balls. The ornamental appeal of these glass balls has been used in weather vanes. The main purpose of these balls, however, is to provide evidence of a lightning strike by shattering or falling off. If after a storm a ball is discovered missing or broken, the property owner should then check the building, rod, and grounding wire for damage. Balls of solid glass occasionally were used in a method purported to prevent lightning strikes to ships and other objects. The idea was that glass objects, being non-conductors, are seldom struck by lightning. Therefore, goes the theory, there must be something about glass that repels lightning. Hence the best method for preventing a lightning strike to a wooden ship was to bury a small solid glass ball in the tip of the highest mast. The random behavior of lightning combined with observers' confirmation bias ensured that the method gained a good bit of credence even after the development of the marine lightning rod soon after Franklin's initial work. The first lightning conductors on ships were supposed to be hoisted when lightning was anticipated, and had a low success rate. In 1820 William Snow Harris invented a successful system for fitting lightning protection to the wooden sailing ships of the day, but despite successful trials which began in 1830, the British Royal Navy did not adopt the system until 1842, by which time the Imperial Russian Navy had already adopted the system. Nikola Tesla's U.S. patent 1,266,175 was an improvement in lightning protectors. The patent was granted due to a fault in Franklin's original theory of operation. The pointed lightning rod actually ionizes the air around itself, rendering the air conductive, which in turn raises the probability of a strike. In 1919, many years after receiving his patent, Dr. Tesla wrote an article for the Electrical Experimenter entitled Famous Scientific Illusions, in which he explains the logic of Franklin's pointed lightning rod and discloses his improved method and apparatus. In the 1990s, the lightning points were replaced as originally constructed when the Statue of Freedom atop the United States Capitol building in Washington, D.C. was restored. The statue was designed with multiple devices that are tipped with platinum. The Washington Monument also was equipped with multiple lightning points, and the Statue of Liberty in New York Harbor gets hit by lightning, which is shunted to ground. Lightning Protection System. A lightning protection system is designed to protect a structure from damage due to lightning strikes by intercepting such strikes and safely passing their extremely high currents to ground. A lightning protection system includes a network of air terminals, bonding conductors, and ground electrodes designed to provide a low impedance path to ground for potential strikes. Lightning protection systems are used to prevent or lessen lightning strike damage to structures. Lightning protection systems mitigate the fire hazard which lightning strikes pose to structures. A lightning protection system provides a low impedance path for the lightning current to lessen the heating effect of current flowing through flammable structural materials. If lightning travels through porous and water-saturated materials, these materials may literally explode if their water content is flashed to steam by heat produced from the high current. This is why trees are often shattered by lightning strikes. Because of the high energy and current levels associated with lightning, and the very rapid rise time of a lightning strike, no protection system can guarantee absolute safety from lightning. Lightning current will divide to follow every conductive path to ground, and even the divided current can cause damage. Secondary side flashes can be enough to ignite a fire, blow apart brick, stone, or concrete, or injure occupants within a structure or building. However, the benefits of basic lightning protection systems have been evident for well over a century. Laboratory-scale measurements of the effects of any lightning investigation research do not scale to applications involving natural lightning. Field applications have mainly been derived from trial and error based on the best intended laboratory research of a highly complex and variable phenomena. The parts of a lightning protection system are air terminals, bonding conductors, ground terminals, and all of the connectors and supports to complete the system. The air terminals are typically arranged at or along the upper points of a roof structure, and are electrically bonded together by bonding conductors, which are connected by the most direct route to one or more grounding or earthing terminals. Connections to the earth electrodes must not only have low resistance, but must have low self-inductance. An example of a structure vulnerable to lightning is a wooden barn. When lightning strikes the barn, the wooden structure and its contents may be ignited by the heat generated by lightning current conducted through parts of the structure. A basic lightning protection system would provide a conductive path between an air terminal and earth, so that most of the lightning's current will follow the path of the lightning protection system, with substantially less current traveling through flammable materials. A controversy over the assortment of operation theories dates back to the 18th century, when Benjamin Franklin himself stated that his lightning protectors protected buildings by dissipating electric charge. He later retracted the statement, stating that the device's exact mode of operation was something of a mystery at that point. Originally, scientists believed that such a lightning protection system of air terminals and downleads directed the current of the lightning down into the earth to be dissipated. However, high-speed photography has clearly demonstrated that lightning is actually composed of both a cloud component and an oppositely charged ground component. During cloud-to-ground lightning, these oppositely charged components usually meet somewhere in the atmosphere well above the Earth to equalize previously unbalanced charges. The heat generated as this electrical current flows through flammable materials is the hazard which lightning protection systems attempt to mitigate by providing a low-resistance path for the lightning circuit. No lightning protection system can be relied upon to contain, or control lightning completely, but they do seem to help immensely on most occasions of lightning strikes. Steel frame structures can bond the structural members to earth to provide lightning protection. A metal flagpole with its foundation in the earth is its own extremely simple lightning protection system. However, the flag's flying from the pole during a lightning strike may be completely incinerated. The majority of lightning protection systems in use today are of the traditional Franklin design. The fundamental principle used in Franklin-type lightning protection systems is to provide a sufficiently low impedance path for the lightning to travel through to reach ground without damaging the building. This is accomplished by surrounding the building in a kind of Faraday cage. A system of lightning protection conductors and lightning rods are installed on the roof of the building to intercept any lightning before it strikes the building. Structure protectors. Lightning arrestor. In telegraphy and telephony, a lightning arrestor is placed where wires enter a structure, preventing damage to electronic instruments within and ensuring the safety of individuals near them. Lightning arrestors, also called surge protectors, are devices that are connected between each electrical conductor in a power or communications system, and the earth. They prevent the flow of the normal power or signal currents to ground, but provide a path over which high-voltage lightning current flows, bypassing the connected equipment. Their purpose is to limit the rise in voltage when a communications or power line is struck by lightning or is near to a lightning strike. Protection of electric distribution systems. In overhead electric transmission systems, one or two lighter gauge conductors may be mounted to the top of the pylons, poles, or towers not specifically used to send electricity through the grid. These conductors, often referred to static, pilot, or shield wires, are designed to be the point of lightning termination instead of the high-voltage lines themselves. These conductors are intended to protect the primary power conductors from lightning strikes. These conductors are bonded to earth either through the metal structure of a pole or tower, or by additional ground electrodes installed at regular intervals along the line. As a general rule, overhead power lines with voltages below 50 kV do not have a static conductor, but most lines carrying more than 50 kV do. The ground conductor cable may also support fiber optic cables for data transmission. In some instances, these conductors are insulated from direct bonding with earth and may be used as low-voltage communication lines. If the voltage exceeds a certain threshold, such as during a lightning termination to the conductor, it jumps the insulators and passes to earth. Protection of electrical substations is as varied as lightning rods themselves, and is often proprietary to the electric company. Lightning protection of mast radiators. Radio mast radiators may be insulated from the ground by a gap at the base. When lightning hits the mast, it jumps this gap. A small inductivity in the feed line between the mast and the tuning unit limits the voltage increase, protecting the transmitter from dangerously high voltages. The transmitter must be equipped with a device to monitor the antenna's electrical properties. This is very important, as a charge could remain after a lightning strike, damaging the gap or the insulators. The monitoring device switches off the transmitter when the antenna shows incorrect behavior, for example as a result of undesired electrical charge. When the transmitter is switched off, these charges dissipate. the monitoring device makes several attempts to switch back on. If after several attempts the antenna continues to show improper behavior, possibly as a result of structural damage, the transmitter remains switched off. Lightning conductors and grounding precautions. Ideally, the underground part of the assembly should reside in an area of high ground conductivity. If the underground cable is able to resist corrosion well, it can be covered in salt to improve its electrical connection with the ground. While the electrical resistance of the lightning conductor between the air terminal and the earth is of significant concern, the inductive reactance of the conductor could be more important. For this reason, the down conductor route is kept short, and any curves have a large radius. If these measures are not taken, lightning current may arc over a resistive or reactive obstruction that it encounters in the conductor. At the very least, the arc current will damage the lightning conductor and can easily find another conductive path, such as building wiring or plumbing, and cause fires or other disasters. Grounding systems without low resistivity to the ground can still be effective in protecting a structure from lightning damage. When ground soil has poor conductivity, is very shallow, or non-existent, a grounding system can be augmented by adding ground rods, counterpoise conductor, cable radials projecting away from the building, or a concrete building's reinforcing bars can be used for a ground conductor. These additions, while still not reducing the resistance of the system in some instances, will allow the dispersion of the lightning into the earth without damage to the structure. Additional precautions must be taken to prevent side flashes between conductive objects on or in the structure and a lightning protection system. The surge of lightning current through a lightning protection conductor will create a voltage difference between it and any conductive objects that are near it. This voltage difference can be large enough to cause a dangerous side flash between the two that can cause significant damage, especially on structures housing flammable or explosive materials. The most effective way to prevent this potential damage is to ensure the electrical continuity between the lightning protection system and any objects susceptible to a side flash. Effective bonding will allow the voltage potential of the two objects to rise and fall simultaneously, thereby eliminating any risk of a side flash. Lightning protection system design. Considerable material is used to make up lightning protection systems, so it is prudent to consider carefully where an air terminal will provide the greatest protection. Historical understanding of lightning, from statements made by Ben Franklin, assumed that each lightning rod protected a cone of 45 degrees. This has been found to be unsatisfactory for protecting taller structures, as it is possible for lightning to strike the side of a building. A modeling system based on a better understanding of the termination targeting of lightning, called the rolling sphere method, was developed by Dr. Tiber Hoover Th. It has become the standard by which traditional Franklin rod systems are installed. To understand this requires knowledge of how lightning moves. As the step leader of a lightning bolt jumps toward the ground, it steps toward the grounded objects nearest its path. The maximum distance that each step may travel is called the critical distance and is proportional to the electrical current. Objects are likely to be struck if they are nearer to the leader than this critical distance. It is standard practice to approximate the sphere's radius as 46 m near the ground. An object outside the critical distance is unlikely to be struck by the leader if there is a solidly grounded object within the critical distance. Locations that are considered safe from lightning can be determined by imagining a leader's potential paths as a sphere that travels from the cloud to the ground. For lightning protection, it suffices to consider all possible spheres as they touch potential strike points. To determine strike points, consider a sphere rolling over the terrain. At each point, we are simulating a potential leader position. Lightning is most likely to strike where the sphere touches the ground. Points that the sphere cannot roll across and touch are safest from lightning. Lightning protectors should be placed where they will prevent the sphere from touching a structure. A weak point in most lightning diversion systems is in transporting the captured discharge from the lightning rod to the ground, though. Lightning rods are typically installed around the perimeter of flat roofs, or along the peaks of sloped roofs at intervals of 6.1 m or 7.6 m, depending on the height of the rod. When a flat roof has dimensions greater than 15 m by 15 m, Additional air terminals will be installed in the middle of the roof at intervals of 15 m or less in a rectangular grid pattern. Should a lightning rod have a point? This was a controversy as early as the 18th century. In the midst of political confrontation between Britain and its American colonies, British scientists maintained that a lightning rod should have a ball on its end. American scientists maintained that there should be a point. As of 2003, the controversy had not been completely resolved. It is difficult to resolve the controversy because proper controlled experiments are nearly impossible in such work. In spite of the work of Moore, al. Described below, most lightning rods seen on buildings have sharp points. Work performed by Charles B. Moore, al. in 2000 has helped this issue, finding that moderately rounded or blunt-tipped lightning rods act as marginally better strike receptors. Described below, as a result, round-tipped rods are installed the majority of the time on new systems in the United States. To quote, "Calculations of the relative strengths of the electric fields above similarly exposed sharp and blunt rods show that while the fields are much stronger at the tip of a sharp rod prior to any emissions, they decrease more rapidly with distance. As a result, at a few centimeters above the tip of a 20 mm diameter blunt rod, the strength of the field is greater than over an otherwise similar, sharper rod of the same height. Since the field strength at the tip of a sharpened rod tends to be limited by the easy formation of ions in the surrounding air, a field strengths over blunt rods can be much stronger than those at distances greater than 1 cm over sharper ones. The results of this study suggest that moderately blunt metal rods are better lightning strike receptors than sharper rods or very blunt ones. In addition, the height of the lightning protector relative to the structure to be protected and the earth itself will have an effect. Charge transfer theory. The charge transfer theory states that a lightning strike to a protected structure can be prevented by reducing the electrical potential between the protected structure and the thundercloud. This is done by transferring electric charge. Transferring electric charge from the earth to the sky is done by installing engineered products composed of many points above the structure. It is noted that pointed objects will indeed transfer charge to the surrounding atmosphere and that a considerable electric current can be measured through the conductors as ionization occurs at the point when an electric field is present, such as happens when thunderclouds are overhead. The National Fire Protection Association, NFPA, does not currently endorse a device that can prevent or reduce lightning strikes. The NFPA Standards Council, following a request for a project to address dissipation array (TM) systems and charge transfer systems, denied the request to begin forming standards on such technology. Early streamer emission theory. The controversial theory of early streamer emission proposes that if a lightning rod has a mechanism producing ionization near its tip, then its lightning capture area is greatly increased. At first, small quantities of radioactive isotopes were used as sources of ionization between 1930 and 1980, later replaced with various electrical and electronic devices. According to an early patent, since most lightning protectors' ground potentials are elevated, the path distance from the source to the elevated ground point will be shorter, creating a stronger field, and that structure will be more prone to ionization and breakdown. AFNOR, the French national standardization body, issued a standard, NFC 17-102, covering this technology. The NFPA also investigated the subject and there was a proposal to issue a similar standard in the USA. Initially, an NFPA independent third-party panel stated that the early streamer emission lightning protection technology appears to be technically sound, and that there was an adequate theoretical basis for the early streamer emission air terminal concept and design from a physical viewpoint. The same panel also concluded that the recommended NFPA 781 standard lightning protection system has never been scientifically or technically validated, and the Franklin rod air terminals have not been validated in field tests under thunderstorm conditions. In response, the American Geophysical Union concluded that T. E. Bryan panel reviewed essentially none of the studies and literature on the effectiveness and scientific basis of traditional lightning protection systems and was erroneous in its conclusion that there was no basis for the standard. AGU did not attempt to assess the effectiveness of any proposed modifications to traditional systems in its report. The NFPA withdrew its proposed draft edition of Standard 781 due to a lack of evidence of increased effectiveness of early stream or emission-based protection systems over conventional air terminals. Members of the Scientific Committee of the International Conference on Lightning Protection have issued a joint statement stating their opposition to early stream or emission technology. ICLP maintains a webpage with information related to ESE and related technologies. Still, the number of buildings and structures equipped with ESE lightning protection systems is growing, as well as the number of manufacturers of ESE air terminals from Europe, Americas, Middle East, Russia, China, South Korea, ASEAN countries, and Australia. Analysis of strikes. Lightning strikes to a metallic structure can vary from leaving no evidence, except perhaps, a small pit in the metal, to the complete destruction of the structure. When there is no evidence, analyzing the strikes is difficult. This means that a strike on an uninstrumented structure must be visually confirmed, and the random behavior of lightning renders such observations difficult. There are also inventors working on this problem, such as through a lightning rocket. While controlled experiments may be off in the future, very good data is being obtained through techniques which use radio receivers that watch for the characteristic electrical signature of lightning strikes using fixed directional antennas. Through accurate timing and triangulation techniques, lightning strikes can be located with great precision, so strikes on specific objects often can be confirmed with confidence. The energy in a lightning strike is typically in the range of 1 to 10 billion joules. This energy is released usually in a small number of separate strokes, each with duration of a few tens of microseconds, over a period of about 1/5 of a second. The great majority of the energy is dissipated as heat, light and sound in the atmosphere. Aircraft protectors. Lightning protection for aircraft is provided by mounting devices on the aircraft structure. The protectors are provided with extensions through the structure of the aircraft's outer surface and within a static discharger. Protection systems for use in aircraft must protect critical and non-critical electronic equipment. Aircraft lightning protection provides an electrical path having a plurality of conductive segments, continuous or discontinuous, that upon exposure to a high-voltage field form an ionization channel due to the system's breakdown voltage. Various lightning protection systems must reject the surge currents associated with the lightning strikes. Lightning protection means for aircraft include components which are dielectrics and metallic layers applied to the ordinarily lightning-accessible surfaces of composite structures. Various ground connection means to the layers comprises a section of wire mesh fusing the various layers to an attachment connecting the structure to an adjacent ground structure. Composite to metal or composite to composite structural joints are protected by making the interface areas conductive for transfer of lightning current. Some aircraft lightning protection systems use a shielded cable system. These systems consist of one or more conductors enclosed by a conductive shield. The cable has both conductors of one end connected to a grounding element. This is intended to provide protection from electromagnetic interference. Such systems reduce the electromagnetically induced voltage in a shielded conductor. This is intended to provide protection against induced electromagnetic interference from lightning. This network provides a normally high impedance which breaks down to a very low impedance in response to a momentary voltage surge electromagnetically induced in the shield. This establishes a conductive path between the shield and ground. Any surge voltage from lightning creates a current through the cable. This results in an electromagnetic field of the opposite direction, which cancels or reduces the magnitude of the electromagnetic field within the shielded cable. Watercraft protectors. A lightning protection installation on a watercraft comprises a lightning protector mounted on the top of a mast or superstructure, and a grounding conductor in contact with the water. Electrical conductors attach to the protector and run down to the conductor. For a vessel with a conducting hull, the grounding conductor is the hull. For a vessel with a non-conducting hull, the grounding conductor may be retractable, attached to the hull, or attached to a centerboard. Risk assessment. some structures are inherently more or less at risk of being struck by lightning. The risk for a structure is a function of the size of a structure, the height, and the number of lightning strikes per year per meter squared for the region. For example, a small building will be less likely to be struck than a large one, and a building in an area with a high density of lightning strikes will be more likely to be struck than one in an area with a low density of lightning strikes. The National Fire Protection Agency provides a risk assessment worksheet in their Lightning Protection Standard. IEC Lightning Risk Assessment comprises 4 parts: loss of living beings, loss of service to public, loss of cultural heritage, and loss of economic value. Loss of living beings is the most important, and this is the only loss taken into consideration for many non-essential industrial and commercial applications. IEC risk assessment calculations can be very complicated unless done by a software. Standards. The introduction of lightning protection systems into standards allowed various manufacturers to develop protector systems to a multitude of specifications. There are multiple international, national, corporate and military lightning protection standards. NFPA 780, Standard for the Installation of Lightning Protection Systems, M440.1-1, Electrical Storms and Lightning Protection, Department of Energy, AFI 32-1065, Grounding Systems, U.S. Air Force Space Command, FAA 19 Sao Tome and Principe do Brasil, Lightning and Surge Protection, Grounding, Bonding and Shielding Requirements for Facilities and Electronic Equipment, Lightning Protection Systems, UL's Lightning Protection Program, Underwriters Laboratories, EN 62305/IEC 62305, Protection Against Lightning, EN 62561/ IEC 62561, Lightning Protection System Components, IEEE Standards for Grounding, IEEE SA 142-2007, IEEE Recommended Practice for Grounding of Industrial and Commercial Power Systems. ESA 1100-2005, IEEE Recommended Practice for Powering and Grounding Electronic Equipment. AFN or NFC 17-102, Lightning Protection, Protection of Structures and Open Areas Against Lightning Using Early Stream or Emission Air Terminals. See also, Grounding Kit, Václav Prokopdivia, constructor of the first grounded lightning rod, in par and registered trademark Amatus UZNOJMA during 1750 to 1754. James Otis, Jr., contemporary of Ben Franklin, killed at doorway by lightning in Andover, Massachusetts on May 23, 1783. Apollo 12. The Saturn V rocket was struck by lightning shortly after blast-off. Notes. References. External links. Researchers find that blunt lightning rods work best. USA Today, June 10, 2002. Federal Aviation Administration, FAASTD 019D, Lightning and Surge Protection, Grounding, Bonding and Shielding Requirements for Facilities and Electronic Equipment. National Transportation Library, August 9, 2002. Keitel, Richard, Lightning Rods, Recent Investigations. National Lightning Safety Institute, September 26, 2005. Keitel, Richard, Should Lightning Rods Be Installed? National Lightning Safety Institute, September 26, 2005. Keitel, Richard, Fundamentals of Lightning Protection. National Lightning Safety Institute, September 26, 2005. Nelm, Richard L., Lightning Controversy Goes On, The Electrical Apparatus, February 2001. Lightning Safety Alliance Education page, John Scaffern, Orr's Circle of the Sciences, Atmospheric Electricity Euro Theory of Lightning Rods WS or 1855. February 1919 Popular Science article about lightning arresters and how they were used in early AC and DC power distribution systems, electrical devices and how they work, Part 14, Lightning Arresters, Popular Science Monthly, February 1919, 5 unnumbered pages, scanned by Google Books, http://books.google.com/ Books ID equals 7 IG Dambaj ampersand PG equal PT 17